Hi, welcome to Parametric House. In this paracourse lesson, we want to design a parametric Mero joint. As you can see here, we have the pipes as one of the outputs. We have the conic section. So here you can see that we can extract the conic in this tutorial. And also we have the ball, which is going to be the central sphere. And also in this tutorial, we're going to learn how to make the sleeves, which is going to be these connection between the conic and the sphere, and that is going to be the final result. At the end of this tutorial, I'm also going to project the detailing of this Mero joint on the ground, and as you can see here, we can have them as a make 2D component here on the in the Rhino environment. We can put that into layer 1 and layer 2, which is going to be the hidden and the visible, which is really great if you want to use that in your project to maybe add more detailing dimensions. So that is also going to be a little bit of a trick we're going to use at the end of this tutorial. To make this example and tutorial more practical, I'm going to draw a series of lines in Rhino. So assume that we have these lines. We can also bring them up in the Z direction. So they are in a 3D space, or something like this. And we're going to bring them inside Grasshopper. Before I do that, if I hit the direction in Rhino, you can see that all of the direction are correct. To make it a challenge, I'm going to change a series of them. So like these two are in different directions. So we're going to fix that, especially if a user by mistake adds different directions to the list. So I'm going to go to the params menu and pick up the curve, set multiple curves, and bring them inside. Maybe we want to also add another line here. So we can right click and set multiple curves, which are these lines we want to work with. Okay, to find the center of these lines, which is the intersection, I'm going to use the intersect physical and use this multiple curves, which is going to find the intersection between a series of multiple curves. And the reason we are doing this is because it's going to give us a point, which is exactly what we need. And here you can see that it's going to give you 15 points. I'm going to delete all of them and just use one of that. Obviously, you can use a set list item to pick up one of them. Also, there is a tool, I just wanted to add this to the tutorial, that you can use the vector point and call duplicates. Give it to the point and just right click and select leave one. Here you can see that it's also going to give you 1 point, and the 15 is going to go converted to 1. So I'm just going to put that here for educational purposes. But anyway, this is the point we're going to work with as we go forward. Let's make a sphere around it. The best method, I think, is to produce the sphere first. Then we can make the sleeves, and then we can make the conic part, and finally we can make the pipe. Because if you start with the pipe, then how can you find the different planes between the conic and the sleeve and the sphere? It's going to make it really complicated. So I rather start from the center and go back to finish the complete piping method. Okay, now we can go to this surface and use the sphere component. And let's just give this a number slider based on your project. You can just adjust this. And this is the sphere radius. Okay, after we have this one, what we want to do is to make a place for the pipes to sit on, especially for the sleeves. And that's why we have to cut this with a plane. So for example, if I go here and say set C plane, and let's say perpendicular to curve, and select this one, and go and select a place. I think that we can't see it here in Rhino, but anyway, assume that we select here, and I'm going to turn on the O snap and draw a surface, a rectangular surface. Okay, just make this as big as possible so you can see that. And then go the C plane, set the C plane to top. And let's bring that inside. Okay, so if I just say find the boundary between these planes and the sphere, I think that we can do that in Rhino with a trim. So we can just trim this part. Yes. You can see that we want to make this. I can also cap this because it's open. Just cap, and it's going to be closed. We're going to make these parametric in Grasshopper. So how can we do that? Okay, to make this parametric in Grasshopper, what I want to do is to first fix the direction of the lines. To fix the direction, let me show you here with the curve, point on curve. You can see that each of them are in different direction, as I've explained before. We have to fix that. The problem here is that if we use the curve flip the curve with a list item, you can use this technique and say flip it. There is going to be some flipping, so it's going to be some true and falses. But as you can see here, this is not going to solve our issue because it's going to be in the wrong direction. Also, there is a problem that maybe it's inwards and we want to put all of those curves outwards. So let me show you how you can do that with an algorithm. This is just like my method, but I think maybe there are better methods anyway. So what I want to do is to use the curve endpoints and graft each of these start and ends and put them into one container with a shift key. That is going to put, also let's simplify this. That's going to put each of these line points in one group. So we have the first line 2 points, second line 2 points, and so on. Then what I can do here is go to the vector point and use this closest points. We're going to use this searching point, which was the center, and we deleted all of them and just picked one of it for the one which is searching. And we're going to give the 2 points to the cloud. So what's happening here is that this single point, assume that this is like the first group, and we have this as the group 0. Okay, it's going to have 2 points. We don't know the number, but anyways, so this is 0, this is 1. If we say find 2 nearest point, what it's going to do is that this point is going to find this point as the nearest, which is going to give it as the first output, and then it's going to give the second point as an output as the farthest. So this is a technique we can use, and then we can select the second output as the result. So what you have to do here is to say find 2 nearest point. As you can see here, it's going to give you 2, and then I'm going to list items select the second one. Because the first one is the nearest, we're going to just right click and reverse it so it goes to the last one. And this way what we can do is to use a curve line between 2 points and make this with the center towards this one. But remember that you have to also flatten this so it gives you all in one group. So I'm going to just flatten this. If you don't know about these, you be sure to watch the data management section. But anyway, here you can see that the lines are reconstructed, and we can give this point on curve to them, and it's going to all go outwards. So that is the technique I found is useful, especially if you want to fix the direction. So I'm going to save this and you can check it out later. Okay, why did we fix the direction? Because we want to talk about the part we want to make the plane on it, right? To do that, what we have to do is to find the subcurve, and I mean from here to here, which is going to be a line, and then move the plane on this line, right? So you can do that by going to the curve analyzers and use this evaluate length. Now that all of them are in the same direction, you have to put the normalize to false because we want to find a real length here, right? When you put the normalize to true, which is the default state, it's going to make the line like between 0 and 1, and you have to give it a percentage here, but we don't want that. I don't know why the default is the true normalized, but we have to put that to false so we can give a real length here. So I'm going to invert it, and for the length what we can do is to give the same as the radius, and you can see that it's completely sitting on the sphere. And now we can make a line. So I'm going to make a line from the start point towards this evaluated point, and now we can have these inside the sphere. Let's make a perpendicular frame on it. So let's go to the curve analyzers and perpendicular frame, reparameterize it so it's between 0 and 1, and I can give a number slider between 0 and 1 with maybe 2 decimal. This is like a percentage location. Obviously it has to be less than 1 and not 0, because 0 is on the center. So I'm going to give this number slider between maybe 0.6 to 1. And 1 is not going to give you any intersection because it's completely tangent at the sphere. We can just bring that a little bit inside. And if we want to make the cutting with these planes, unfortunately there is not a tool inside Grasshopper to do that. As you can see here, we can find a BREP plane, so we can intersect this sphere with this plane and find the circles, but not to find the real solid. So what I found is the best method is to make a surface on that. So surface, primitive plane surface, and give this frame to the plane. For the size, because it doesn't really matter, it's going to anyway intersect together, but we want to cut it. We have to give this same as the sphere radius. But if we give it to the X and Y, it's going to just go, because it's a domain, it's going to make it from 0 to that number. So you can see it's just going outwards, and this is not correct. So you can do that by going to the math, construct domain, and make it from minus X to plus X, which is plus C anyway. It means that if we have a plane here, it's going to be from minus X to X, and that is going to make it completely in the right domain for both X and Y. And now you can see that it's intersecting with the sphere exactly how we want it. We can just bring it inside outwards anyway. And what we have to do here is to go to intersection, shape, and there is a really good tool which is boundary volume. And you can see that it writes that you can create a closed polysurface from a boundary surfaces. I found that this is useful if you want to say this sphere with these planes and just flatten it if it doesn't give any output, because they have to all be in one group. Now you can see that it's really cool. It's just going to give you these cutting planes on the surface. Okay, now you can see that by changing the T parameter, which I'm going to put for this input, we can change these location. A good thing about this algorithm is that it's completely controllable for any input based on how many lines you have. So for example, here we have I guess 6 lines. We can give 6 sliders by going to the parameters menu and selecting this gene pool. And for example, it's going to be 6 sliders between 0 and 1. I guess 0.5 is better because I don't want to reach 1. And the good thing about this is that you can control each of them. Let's just increase that to maybe 80%. Each of them differently, because maybe there is a bigger pipe here, you want to control that. Oh, okay, this one was the last one. And let's also connect a display custom preview to that so we can see that. I usually also give a BREP edge so I can see the edges better. Now you can see that you can also control each of them separately. Okay, so that is great if you want to have a complete control over the planes, I guess. But if you give it one number sliders, all of them are going to be controlled with not one number slider. Okay, so that is a way we can actually play around with the inputs. So now you can just play around with these numbers to get the final results, and that's it. The next part is going to model the sleeves, so we can put those onto these planes. Okay, for the sleeves, I'm going to pick up this plane or frames here, and we're going to work with these planes to get the final results. For the sleeves, I'm going to use the curve primitive, and we can go with this polygon, which can produce a polygon on a plane. So I'm going to say give a polygon, give it on the plane, and we can give a radius here. So this number slider is going to be the sleeve radius. We can control that easily. Because we are just using this for visualization, I'm going to extrude that outwards. So we can just go to the parameters menu, geometry, surface, connect the surface to it. So it's going to convert to a surface. And then we can extrude it outwards. So surface, freeform, extrude. If you go to the parameters menu and connect a vector to a plane, it's going to give you the normal direction, which is going to be outwards, I guess, because we are using the line here, the plane is going to go outwards, right? So we can just multiply that with a number again, which is going to be the sleeve extrusion. We can say sleeve length. And that's like the second part we can use it. You can bake that in Rhino if you wanted to see the final results, or we can just give this again a custom preview with a brep edge so we can see it. A swatch also is useful. I usually use this color picker and use the Rhino color so it feels more native. And for this one, we can give any color we want. Anyway, now we can control the radius. Remember that we can control that, and we can also control any of these planes if we want to put them in different cutting planes. Okay, now that we have the sleeves done, what we have to do is to move, transform, move, and move this plane with the same vector outwards. So it's going to sit on the sleeves, and now we can make the conic part. So for the conic part, I want to make a circle, so curve, circle radius. Now we can control the radius. Again, I'm going to pick up a number slider, and this one we can say conic radius end. So that is the radius end. And again, we can move this plane with the same multiplication and bring it outwards, right? For the outwards part, this is going to be the length of the conic part. So we can say conic length. And again, just make a circle on it. This time, this second circle, which obviously has to be a little bit bigger, is going to be the pipe radius. So it's going to be pipe radius. And we can have that. We can just turn off the planes. And what we have to do is just connect them. So we have control over the length, the radius at the end, the radius at the start, which is going to be the pipe, and we have to loft these together. Surface loft. And if I use the shift key to add these together, you can see it's going to connect all of them together. What I usually prefer to do, and it's a good exercise, is to put the same container, which is a curve at front, use the shift key to add them, and graft each of them when you want to just do that, like group of 2, group of 3, graft each of them. Also simplify, solve some issues because we have some extra zeros. So just graft and simplify, and check this out. If the input is like 2, that means that we want to loft like 6 times with 2 sections. Remember, so this number of groups means that how many times we want to do it, and this one is going to means that how many times we want to connect those together. Okay, so that if I give that to the loft, you can see it's happening. We can also use a surface cap holes to cap it, and now we can just say, if I bake this, you can see it's a complete solid here. So now we have control. We can again give this brep edge custom preview to this, and give it whatever color you want. This is going to be the pipe radius. This is going to be the sitting radius. This is going to be the length. That's it. And now that we have this circle here, we have to also fix it with the pipe. So I'm going to pick up the center, just give a point, it's going to find the center. We also have to find the end points. We did it here with the closest point. If you remember that we had picked the farthest part of the point, so I'm going to bring that here too. And because this is in groups but this is not, I prefer to flatten this one. So both of them are in same group, and then we can use a curve line to make this last part as a line, and then we can give the pipe. So just go to surface, pipe. The radius is going to be the same as the pipe radius we had here. And then you can use a cap at end, which is flat. I think it's good for visual purposes, but visualization purposes, and then I'm going to just give that to the pipe. And that's it. Now we have also the pipes. If I bake that, you can see that we have the pipes too. That's it. Now we have a complete parametric view of these details. We have the sphere radius. We can control the planes. Let me just find this one, which is we are seeing here, as you can see here. We have control over the sleeve radius and the sleeve length and the conic length and the conic end and the conic and the pipe radius, like this. So that is going to give us the final result, and we can use it in our project. Good thing about this is that you can also use that for detailing. So if you want to, you can go to display dimensions and use this make 2D component. The make 2D component is that the geometries you want to make them into, put it on the ground. So here we can just put all of them into one B-rep. I'm going to just say we have the pipe, the sphere, and we have the sleeves. We have the conic part, and we have the pipes. We can flatten all of them. I'm going to make this wire display hidden so it doesn't intersect with this project, and we can give that to the geometry we want to do. The clipping plane has to be defined, so go to the display dimension and some clipping plane here. Make 2D parallel view, make 2D perspective view. The camera position, we have to give it a point, so I'm going to just set a point here and assume that we are looking at it from here. The projection frame, which is going to be the frame we are looking at, we can say that obviously this has to be in the normal direction, but I'm just going to give that to a rectangle. We can bring that as a curve and give that to the view. Okay. So as you can see here, it's automatically finding the normal direction of that. I guess even if I rotate that, it's going to move the location of the camera a little bit in a different place. So I don't think that this point is going to affect, it's going to project it on the normal direction anyway. So that is also a good exercise. I'm just going to internalize this for you so you can use it later. And then we can just say compute. And it's going to put it on the ground, which is really great. Clipping plane, optional clipping planes, we don't want that. You can say that we have these visible curve. Let's just bake that into layer 1. We have this hidden curves. Let's bake that into layer 2. And here you go. You can just have them in Rhino, which is a really great way to make the details. So maybe you want to turn off the hidden layer. You can see that how great it is. It's a really fast way to bring it on the ground. So that is the Make 2D component, and I hope this tutorial was useful. If you have any questions, just ask below this lesson. Thanks for watching. See you next time. Bye.